In this video, we solve an integral equation using the Laplace transformation. This is actually very similar to solving an initial value problem using the Laplace transformation method. The only difference is that our equation does not just contain derivatives of an unknown function. With an integral equation, the equation contains integrals involving an unknown function. So our unknown function in this case is the function f of t. Notice we've got tau of f of t minus tau d tau in this integral over here. So that's going to be something that we can write in terms of a convolution. And because we have the convolution theorem, we'll be able to take the Laplace transformation or the Laplace transform of that convolution of two functions. So we just start in the same way that we always do. We're going to introduce our notation. We're going to let the Laplace transform of little f be big F, so everybody knows what we're talking about. We just start using the letter capital F. And then we compute the Laplace transform of the integral equation. And the Laplace transform is an integral operator, so it's linear. So we have the Laplace transform of f of t on the left-hand side equals the Laplace transform of t times e to the t, plus the Laplace transform of the integral from 0 to t of tau times f of t minus tau d tau. Now the Laplace transform of f of t is f of s by definition. And the Laplace transform of e to the at, this is just from our table, or t times e to the at, is 1 over s minus a squared. In our case, the coefficient of t in that exponent is 1. So this is going to be 1 over s minus 1 squared. Now to compute this, we need to remember the definition of the convolution. And that's this. It's the integral from 0 to t of f of tau times g of t minus tau d tau. Don't let the letter choices bother you. I'm going to call this one f and this one g. The important part here is that you've got a function of tau and a function of t minus tau. In our case, our function of tau, I'll think of this as g of tau times f of t minus tau this time. G of tau is equal to tau, and f of t minus tau is just f of t minus tau. So we have the convolution of g of t with f of t. Since g of tau is equal to tau, we have g of t must be equal to t. And of course, if f of t minus tau is itself, then f of t is just f of t. Doesn't really tell you anything. But we see that this is the convolution of t with f of t, so we can write that way. Got the Laplace transform of this convolution. And the convolution theorem tells us that the Laplace transform of a convolution is just the Laplace transform of the first factor times the Laplace transform of the second factor. So we'll have f of s times g of s, as we discussed in the last video. So we will have f of s here plus 1 over s minus 1 squared. And we're adding the Laplace transform of t to the first. That's going to be a 1 over s squared times the Laplace transform of f of t, which is f of s. Now, just like when we're solving an initial value problem using the Laplace transformation method, after we take the Laplace transform of the integral equation and simplify, then we just want to get f of s by itself, and then we want to take the inverse transform of f of s to get f of t back. So we just want to solve for f of s next. That means I need these both on the same side, so I will subtract 1 over s squared times f of s from both sides. And I'll factor out that f of s in this case. And rather than dividing this fraction by this fraction and having to deal with the complex fractions, what I would recommend you do is get a common denominator over here. So write that 1 as an s squared over s squared, and write that as a single fraction. So you'll have s squared minus 1 over s squared. And then when you want to get f of s by itself, rather than dividing by this fraction, multiply by the reciprocal of that fraction. So we'll multiply by s squared over s squared minus 1 on both sides. And when we do that, the s squareds will reduce, the s squared minus 1s will reduce, and we'll have this. So we have f of s equals s squared over this guy right here, s minus 1 squared, and s squared minus 1 can be written as s plus 1 times s minus 1. We've got s squared over s plus 1 times s minus 1 cubed. Now at this point, you've got options. We could use some kind of convolution theorem in reverse rule. We could think of this as a product of two convolutions, but I would rather not. I think the easiest way for me to handle this is to use the partial fraction decomposition. So I would rewrite this using partial fraction decomposition. So we just did some algebra, we got f of s by itself, and now we're going to use partial fractions here. So I've got s squared in my numerator, and I'm dividing by s plus 1 times s minus 1 cubed, and it has this decomposition. It's going to be a constant over s plus 1 plus a constant over s minus 1 plus a constant over s minus 1 squared plus a constant over s minus 1 cubed. And the reason that we're doing that is because we've got two linear factors. One of them appears 3 times. So if that linear factor s minus 1 appears 3 times, you have 3 terms in the decomposition. S minus 1 to the first, s minus 1 to the second, s minus 1 to the third are in those denominators. And since they were linear factors, we have constants a, b, and c, or b, c, and d in the numerator for those. Okay, so then we take this guy. This is the partial fraction decomposition for values of a, b, c, and d to be determined by s. And if we want to find a, b, c, and d, we multiply by the LCD, which is always the original denominator. Okay, and then you reduce, and all of the fractions will be gone. One of the s minus 1s reduces there, and then 2 of them reduce there, and then all 3 of them reduce there. And so we get this. S squared equals a times s minus 1 cubed plus b times s plus 1 times s minus 1 squared plus c times, we've got s plus 1, s minus 1, and then we've got d times s plus 1. Now, typically we choose values of s that will cause each of the factors to be 0, and that will help us to solve for some of these constants a, b, and c, but we only have 2 factors that are unique, so we're going to have to choose other values of s as well. So when s is equal to 1, one of those factors disappears. If s is equal to 1, this is a times 0, this is b times 0, and this is c times 0. The only one that does not have a 0 factor is this d. So if s is 1, we'll have a left-hand side of 1 squared, which is 1, and the right-hand side is d times 1 plus 1, so 2d. So d must be 1/2. And then if s is equal to -1, that's when s plus 1 equals 0. So if if s is -1, I've got b times 0 here, and c times 0, and d times 0. The only one that does not have a factor of 0 multiplying it is this a value. -1 squared is -1 times -1, which is +1. And then I'll have -1 minus 1 is -2 cubed. So I've got -8 times a there. So A is negative 1/8. So we weren't able to get A, B, C, and D, but we were able to get A and D by choosing values of S that cause each of those factors to be 0. Now we need to find B and C somehow, so we just pick other values of S. I would choose S equals 0, and then use the fact that A and D are known to find maybe a system of equations involving B and C. We'll see what happens. If S equals 0, we have a 0 on the left-hand side equals A times negative 1 cubed, which is negative 1, so negative A, plus B times 1 times 1, so that's just B, plus C times 1 times negative 1, it's negative C, plus D. And A is negative 1/8, so this is going to be positive 1/8. And D is 1/2. Multiply by 4/4, and so we have 4/8 plus 1/8 is 5/8. So we have that. Or if we solve for B minus C, we get B minus C must be negative 5/8. Okay, so that's one equation with two unknowns. Let's get another equation with those two unknowns. Pick any value of S you want. I would choose 2 next. 2 squared is 4. So I'll have 2 minus 1, which is 1 cubed times A, plus B times 2 plus 1 is 3. 2 minus 1 is 1. 1 squared is 1. And we have C times 3. 2 minus 1 is 1. Plus D times 3 as well. Okay, and we know that A is negative 1/8. And I've got 3B and 3C here now. And D is 1/2, so this is going to be 3/2 multiplied by 4/4. So I've got 12/8 minus 1/8. So it's 11/8. And over here, I guess we could write that as 32/8. Oops. So if we are trying to get 3B plus 3C by itself, we'll subtract this 11/8 from both sides. 32 minus 11 is going to be 21/8. And then if we want, we could divide both sides by 3 as well. And we would end up with B plus C equals 7/8. Okay, so we've got B plus C is 7/8 and B minus C is negative 5/8. We could use those two together to solve for for B and C. Now I know that calculators can solve systems of equations like that, but if you are at TCC and you don't know how to solve systems of equations, systems of 2 equations and 2 unknowns yet, I really want you to learn how to do it by hand, because if you can't do it by hand by the time you leave TCC, then something is wrong. It's a very important skill. So B minus C is negative 5/8 and B plus C is 7/8. So let's add those two equations together, and we get 2B equals 2/8, which is 1/4. And if we divide both sides by 2 or multiply by 1/2, same thing, we get B equals 1/8. And if B equals 1/8, and then we have B plus C equals 7/8, then we have C must be equal to 6/8, which we all know is this. 6 is 3 times 2, 8 is 4 times 2, so C is 3/4. And if you're saying to yourself, what are we doing again? Remember, we're trying to write f of S in a different form. F of S was this right here, or it can be written as a sum of these 4 factors, or sorry, 4 fractions, not factors, where A, B, C, and D are the values that we just found. So we're going to have A equals negative 1/8 over S plus 1. plus b over s minus 1 plus c over s minus 1 squared plus d over s minus 1 cubed. C was 3/4, it's A, B, C. B was 1/8. And what was D again? D was 1/2. Okay. Now, if we go to our table, we've got an inverse transform for this in our table. That's s minus a with a equals -1. So the inverse transform of that is the -1/8 times the inverse transform of 1 over s minus a, which is e to the at. A is -1, so it's going to be e to the -1t. This is similar. We have 1 over s minus 1, so a is +1 in that case. So the inverse transform of 1 over s minus 1 is e to the at, where a is +1. Now this one is similar, but it's got that s minus 1 squared. The inverse transform of 1 over s minus 1 squared is this. It's t times e to the at. So we're going to bring that 3/4 down. In our case, a is 1. So we'll have t times e to the 1t. And for this one, well, that looks like this. You've got the inverse transform of n factorial over s to the n plus 1 is t to the n, but then the s has been replaced by an s minus 1. So if we have the inverse transform of n factorial over s minus a to the n plus 1, that should be t to the n times e to the at from our first translation theorem. I believe that's in the table as well if you were not comfortable just deriving that. But I see that pattern here. If n plus 1 is 3, that means n is 2. So I need a 2 in the numerator. 2 factorial is 2. So I'm going to multiply by 2. That's legal as long as I also divide by 2, and I will factor that 1/2 out. So we're going to have 1/2 times that 1/2 is 1/4. And the inverse transform of 2 over s minus 1 cubed is going to be, well, since n equals 2, t squared times e to the at. And a is the number we're subtracting from s, so a is equal to 1. So we've got that right there. Now, if you want to, you could factor out a 1/8 from everything. You don't have to, though. Maybe I'll factor out -1/8. And if I factor out a -1/8 from this, I'm going to have a -6 here because -6 over -8 is +3/4. And over here, I would have a -2 over -1/8 to get a +1/4. And I see that each of these terms has an e to the t in it. So I could factor that out from everything. So it's e to the t times 1 plus 6t plus 2t squared if I factor out the negative as well. Okay, so that's our f of t. I'm not going to prove it here, but the process that we just followed leads us to finding this solution to the integral equation. And all of that involved was this. It was very simple. We define our notation. We take the Laplace transform of the integral equation. We solve for f of s, and we take the inverse transform. That required some partial fractions. And then once we did the partial fractions, we would look expressions like this up in the table or derive the inverse transforms of that using the theorems that we're familiar with, like that first translation theorem. And then we compute the inverse transform. So I guess that was my last step. And if you're saying to yourself, what did I just find? This is a function f of t. If you substitute it into this integral and evaluate this integral and you add t times e to the t to that, it turns out you actually get f of t back. That's what it means to solve an integral equation.